Yeah, thank you for the introduction. Yeah, those of you who know me probably know me as somebody that does MDO, but mostly airplanes. So today is a bit of a different talk. And it's actually not work or research that was done. Michigan is mostly work part of a consulting work for American Magic together with some students. So Erica Johnson, Andrew Lemkin, Yingsheng Liao, Galen was here, and Neil Hildred. And also on the American Magic side, I want to acknowledge Harold Youngren, who was the main point of contact there and provided us a lot of the guidance for this work. Towards the end, I also mentioned some University of Michigan research that was a precursor that made this possible, and acknowledge that as well. This is me, like in Azores, sailing. And I think it was then that I got kind of a feel for aerodynamics and hydrodynamics. You got the aerodynamics of the sail, you got the dynamics on the water, you got that feel of the driving force of the sail and the drag on the water. And I just really like that feeling that and trying to understand it. And I remember the early explanations of how a sailboat works, and I never quite was happy with that. So I think that's part of the reason I got fascinated by aerodynamics and hydrodynamics. When you have a little boat like this, it's not very efficient. You can see just from the shape, it's very boxy. It's mostly for cheap manufacturing. And there's a lot of drag, right? And wave drag is one of the major barriers, right? You have wave drag, but you also have just the skin friction there. So that's a major component, is skin friction. Then you have wave drag, and that goes up quadratically with the speed, right? So that's a major barrier for boat speed. Well, what if you could take this little boat? It's called an Optimist. It's a Olympic class boat, and just raise it off the water. Now the hull is completely off the water. You get rid of most of the weight resistance, right? And what's keeping it up is basically a wing underwater, right? That's lifting the boat up, right? So now you have an added, as you know, in aerospace engineering, you have induced drag that never produced lift. So you have an added induced drag that you didn't have before, right? But you get rid of all the drag from this. Now you get aerodynamic drag, but that's way less, right, than the drag on water. And so this is where foiling comes in, and this has been a revolution in recreational and also commercial boats, at least up to a certain size. And you can see here some body wing foiling. That's basically a small airplane underwater that's sustaining that whole weight, right? But because water is 8 times more dense than air, you can get away with much smaller surfaces, right? And here you can see the advantage in terms of seat keeping, right? For hydrofoils. Of course, there's a limit there in terms of the weight and so on, and the unsteadiness is an issue. So this takes us to America's Cup. So that's the oldest sports trophy in the world. And this is like the Formula One for sailing, right? And it has evolved a lot over the last several decades. But one of the big revolutions was hydrofoils. So lifting the hull off the water, designing hydrofoils, and so on. And the previous cycle, or the cycle before this new configuration, was actually a catamaran on hydrofoils. But this, in my opinion, much more elegant and a good progress in terms of configuration, where you have a monohull, so a single hull, and you have these 2 arms that you see here, each with a foil. And they alternate sides depending on the tack. You have one side supporting the whole weight and the other counterbalancing. So let me explain the forces here a little more carefully. So the boat has a weight shown here, right? And that's the main weight there. This is also pretty heavy. So as it happens, it's 1.4 tons of weight. This is solid steel here, okay? And the main thing with sailboats is that there's this huge moment created by the sail. So the sail is providing the driving force for the boat. So there's a lot of force there. And some of that force is lateral, right? So we'll tend to heel the boat, right? So that's why you see sailboats, all the older, the more wind you have, the more heeled over they are, right? So you need to fight that somehow. And the regular boats, conventional boats do it with a keel. There's a keel that goes down, there's a big weight, and some of them even have a swinging keel, right, that goes over to provide more moment. This is not the case here. There's no keel because the whole thing is on, the whole weight is on one toilet. And you can see here, this is approximate and proportional. You see this huge vector here, that's the vertical component is basically the whole weight of the boat there, okay? But then you need side force too, but that has it because the oil is canted, provides a side force, counteracting the side force of the wind, okay? So this whole thing needs to be in equilibrium, and it is to lift the whole thing out of the water. Then you have a rudder, which functions a bit like tailing an airplane, that provides the basically trimming and needs to be stable as well. And that's a relatively, just like in airplane wings or airplane configurations, it's a pretty small force there, okay? So that's how the whole thing equilibrates. And having this huge side force is a big help, and having this big weight here with a very long moment arm really helps. So now instead of heeling over, this thing just flies straight. In fact, it heels a little towards the wind. That's the optimal angle there, okay? So in my opinion, a very elegant configuration, because it always bothers me, this heeling that basically translates to inefficiency aerodynamically, right? So you can fly straight like that. And if you haven't seen yet, I encourage you to check videos of this going around on YouTube, not right now. Okay, so where do we come in? Well, first we need to have the tools to analyze. So this is, in this case, CFD, right? It's brand CFD. And if you have the tools to simulate, you can try different shapes, different airfoil shapes, even structural sizing and so on, and then figure out what the drag is, what the velocity made good is, which is the velocity to where you actually want to go in sailing, and so on. But that could be a very tedious process if you're doing manual changes. And this is where the research that we've done in the NGO lab comes in, is into numerical optimization. So coupling these simulations with numerical optimization to automate the design process, okay? One of the main tools we developed over the last several years is the MAP framework. This is an open source framework for aerodynamics, or in this case, hydrodynamic shape optimization. And there are several modules here. One is the optimizer. So this is going to decide what shape you're going to have, right? In this case. And then there's a geometry parameterization module that's going to parameterize the geometry, right? To keep track of this geometry. After changing the geometry, we have to propagate that change to the volume mesh. So we're doing CFD, so we have a mesh over a big volume. And then we have our CFD solver. And finally, the crucial part here, this adjoint solver, this computes the sensitivities or gradients of drag, lift, moments with respect to all the shape variables. And this is the key here to enable all of that we're doing. I won't get into that, but if you want more details, you can check section 6.7 in my book, which is free, by the way. I'm not trying to sell anything. Well, if you buy it, I won't complain. So that's the framework, right? And that's what we're going to use here. Again, there's a lot more details. You can check the papers and so on. So what can we do with this? Well, this is one of the things we can do. Let's say we have a circle. Circle, in terms of drag, is horrible. Lots of drag, and by the way, no lift. The opposite of what we want. We want a certain lift with minimum drag, okay? So we're gonna throw this in our framework and ask, I want to minimize drag for getting lift, right? And this is CFD on it, by the way, lots of separated flow. And the optimization automatically put the figures out that flattening the shape is the way to go. That reduces the profile drag right away. It then figures out that the leading edge should be rounded, the trailing edge should be sharp, right? And by the way, because it's a transonic condition in air, it flattens the top to reinvent the supercritical airfoil. It took NASA many years to invent this, but this basically reinvented the supercritical airfoil with no bias towards this shape at all, except we were a couple of decades later to claim any credit here. But it's still good to see it reproduces a result that was found before. We can also do 3D, and we can even start with very bad designs like this one here, even some of the instructors can tell that these aerodynamics are not so good, right? And when we throw this at the optimizer, it does smooth everything out. And eventually you can see here that the isobars become parallel. It gets rid of any shocks and retrieves elliptical distribution. So this is a nice benchmark. And we've written a lot of papers on this. If you're interested in this, I encourage you to read this and other papers. So I think in part because of the success stories and papers we've written on this, I got called by Scott Ferguson from the chief engineer from American Magic to ask me, okay, can you help us with the design? I was frankly a little concerned, okay, because hydrofoils, we've been doing some work in hydrofoils, but the American Magic, the whole design process, very demanding in terms of pace, and also you require very mature tools, right, and very mature process to really keep up with the whole design cycle, right? So what I said is, well, let's start with a 2D problem first, all right? So that's tip 1.4 in my book, easy to the problem, okay? Start with the solve problem you know you can achieve, and then build up. I use that advice, well, I try to use it every day, and I give it every day too. It's easy to ignore. So I said, yeah, I think we can do 2D at least to start with. And so we did. There are a few different things there, and I'll explain that. But basically, if you look at the whole boat, we're looking at the cross section here. And this section, this foil that I showed before from the back view, right? It has a flap. The flap runs through the whole span, okay? And this flap has an optimal position for each condition, right? So they're constantly trimming that. So that's going to be one of our design variables, okay? As well as the shape. And then we'll have to consider multiple conditions. So I want to thank Scott Ferguson and American Magic for taking us in and giving us the privilege of working with them on this. So when it comes to hydrofoils, we have also, I want to add, our point of contact, Al Youngren, was really key here because he understood our tools, and we were able to do something productive because he had a much better view of what's happening in the overall process for the design. Because it's a really humbling experience to see the whole design process that's going on. There's a sales, there's a hull, and we're doing a tiny part of the hydrofoils, although it's a very critical one. So for hydrofoil design, we can look at the drag polar, just like we do for aircraft, right? But the drag polar and the drag polar is a similar shape, right? But the design implications are a bit different. So you can think of aerodynamic or hydrodynamic shape optimization and design as shaping the drag polar, right? And different parts of the drag polar have different implications. For example, at the bottom here, we have the low CL. If you push it here, you're going to have greater top speed, right? Because it is CL at the higher speeds, right? Here, it would be in the middle, more range or speed. And there, at the high lift condition, we're looking at taking off. So one of the critical things with these America's Cup boats is if they fall off the foils, they're toast, okay? They're just like literally dead in the water, okay? Because it's an order of magnitude more speed on foils, right? So making sure you don't fall off the foils means you need a minimum lift coefficient condition there for maneuver, right? Also in maneuvers is when you tend to fall off the foils or when the wind is too low. So you're looking at, and you'll see a condition that's at lower speed, a higher CL. The thing is, you can't just arbitrarily push this here, here, and here all simultaneously. There are trades to be made. Typically, when you have an already good hydrofoil, if you want to push here, you have to sacrifice here. So a total question of optimal trading between different conditions, right? You might say, oh, I want the maximum lift possible. Well, you're going to have to pay here. So you better just get the lift you need, right? You're not going to get maximum. So this is what optimization can help. So to do this in 2D, we parameterize the shape with the freeform deformations. Again, I won't get too much into the method, but if you look at this, you get the idea. We create a volume that contains the shape, and then we move points at the surface of the volume that affect everything inside. You can see it affects everything inside in a certain way, right? So these are the shape variables that we're going to use. And then we also need a separate one to control the flap, okay? So this is the movement of the flap. It took quite a lot of work to get this just right, because we want to exactly emulate the shape of the physical system. They have a hinge there, they have a bit of a flexible area there, and we want to emulate that shape as best as possible, because very small changes make a big difference in the fluid flow. So we got that. And that's optimized for each condition. Okay. Another thing that's different from what we've done before is cavitation. And we had done some research with cavitation constraints already, so we could use that. So cavitation is basically when the pressure is low enough, right, below the vapor pressure, bubbles of vapor form, all right? And you can see them here. And that's bad in our case because they increase the drag and reduce the lift, okay? They can also cause damage and so on, but we're not worried about that in this case. So how can we avoid cavitation? Well, what we did was to formulate a constraint that limits the pressure, and I'll show you that in a second. So for cavitation, it helps to look at one of these two diagrams. So you can either look at CL versus min CP, but you can convert the CP to cavitation, and this leads to this kind of diagram called the cavitation bucket. So basically it's showing in here you have no cavitation, so this is where you want to operate, and this is the edge of where you can operate, right? And then outside you have different types of cavitation, and you want to avoid those, okay? So like the drag polar, there are different traits there, and like the drag polar, you typically cannot push here without sacrificing somewhere else, okay? And we're worried about cavitation in all parts of the bucket here, okay? And as you'll see, we're able to push that forward in an optimal way. To constrain cavitation, we developed a smooth constraint on the minimum pressure coefficient using an aggregation function called Krasmeyer-Steinhauser. We've used that widely for many different applications, and this is the formulation. And the idea is if you have two constraints, right, and this is the objective function, we can see that the pink areas here are forbidden, so you need to be in this area of the two constraints to satisfy both constraints in a white area. And this would be the exact optimum, right? You can graphically see that. But there's a little kink there, right? That's not smooth. So what we do is with this KS aggregation, it becomes smooth. Now it becomes a bit of an approximation, but if you increase this by a value large enough, this approaches that, right? And we found it was not too conservative. And the final result is that if we draw a line here and say the pressure needs to be under this line, the optimization does successfully go below the line, all right? And you'll see that in our results. So that's how we enforce no cavitation. Okay, a little lesson in sailing for those of you who don't know about sailing. Let's say the wind is coming from top to bottom and you want to sail in different directions. Well, first of all, you cannot sail directly upwind, okay, just impossible. Unless you have a turbine, okay, you can check a car that does that. That's another separate story. But with sails, you cannot. So there's a limit in the angle, okay? And of course, you can still straight downwind, and the position of the sail, the optimal position of the sail varies with the wind direction, all right? And that leads to what's called the sailing polar, okay? The sailing polar on the vertical axis, there's the boat speed here, okay? And this is the angle. So a vector going from here to here actually shows this is the direction and magnitude of velocity of the boat, okay? And then you might want to go here or there. You cannot go further upwind, okay? Because it's too much of a small angle with the wind. You cannot produce a driving force. right? And this is actually data from the America's class boats, but you also see that there's no polar here, okay? You could actually go that way, but it's not very efficient. And I'll explain why in a second. But what you can see here is that this boat is so efficient that it can go up to 4 times the speed of the wind, okay? Which seems counterintuitive. You think of downwind, maybe it's the maximum speed you can get, and you get the speed of the wind, and that's it, okay? But I'll explain there. So these are different lines for different wind speeds, and you can see you get greater boat speed with greater wind speed, which is expected. And the maximum speed is about 120 degrees, okay, relative to the wind. But it's still going pretty fast, close to the wind, okay? All right. So, yeah, let's look at a boat going directly downwind. So the wind is from the back. You put your sail like this, and you need more like something like a flat plate, right? And there's some drag from the hull, right? But what's propelling the boat is just drag from the sail. That's it, right? So there's a limit there in terms of the speed, because you can only go as fast as the wind. Actually, be lower because of drag and so on, right? So you cannot go faster than the wind, okay? The difference is now when you use lift, okay? And this is a little experiment, and thanks to Galen for finding this one, because he gave me a nice mental model to explain this. So yeah, you have a wind tunnel, wind is coming that way, and you'll see that basically, if you provide wind this way and this is on the track, the lift is directly up, and it provides a component along the track, okay? So this is assuming it is on the track. But what's the track on the sailboat? It's the water and the, basically in this case, the foils, but the keel will provide the side force. So it's like it's on a track. It's not as efficient as a track, but it's a sort of track. So, okay, this leads to these diagrams here. So this is a bit simplified, but I think as a major component, you have your boat. The wind is coming this direction, right? And you can get a certain speed in that direction, 30 degrees or so. That's like more or less the closest you can get to the wind. What happens here? Well, we have a sail that produces lift. So this is perpendicular to the wind here. There's a drag on the sail. So the driving force, the force is this way, but there's still a component in this direction, which provides driving force, okay? So like airplanes, you want the least possible drag. We want a lot of lift, right? And there's also some drag of the hull, lift of the hull. So in our mental model for the track, we can see the track here and say the airfoil is fixed, like I showed in the movie, right? And we got the wind coming in this direction. Now we have a lift that's perpendicular to this wind, right? We have a little drag there. I was generous with L over D, okay? And we have the total force. And now we project this force onto the track and we get the driving force, okay? So we can see we get the thrust, and this can go forward, and it goes against the wind. But now we're missing something in this diagram too, which is that the apparent wind changes, because now we are going against the wind. So now we need to add whatever velocity you're going up, we need to add to get this apparent wind, okay? And what happens is that the apparent wind is going to increase relative to the wind, right? And so you get more lift, but you also get the lower angle of attack, okay? And you still get the projected driving force. Now, as this speed increases, right, eventually this gets to equilibrium where you have no driving force, or the driving force is equal to the friction on the track, right? But that limit is such that you can get multiples of the wind speed. So this V, you get multiples of the wind speed, okay, depending on the efficiency. So the more efficient the sailboat, the lower the drag and so on, the more of a multiple you get there relative to the wind speed. But this is how you get it. It's just a question of adding all the forces and getting the driving force. All right. Okay, so now back to our optimization problem. And yeah, we're going to show you a couple of optimization problems. But as with everything, optimization, there's a whole sequence of different optimizations and studies that were done to get this to work well. But in the end, it worked very well where we could do many different studies. And so what we're doing is minimizing the drag, cumulative drag coefficient for different conditions, in this case, sailing conditions, 6 of them. We're going to vary angle of attack and also flap angle and the shape. So we have a total of 40 shape variables. So total number of design variables is 52. And then we have several constraints. We have target lift coefficients for a condition. We have, for the maneuver point, we have a minimum lift coefficient. And then we have this aggregated cavitation constraint. We also have a thickness to chord ratio. So we limit the thickness to chord ratio to be above a certain amount because for structural rigidity and integrity. We also have area and thickness constraints, okay? And the points we considered, these were given by the American Magic team. They have a code called VPP, the Velocity Prediction Program, right? That basically simulates different conditions of sailing. And they're able to tell us these are the conditions we care about. So we have 3 upwind conditions, 3 downwind conditions, and 1 maneuver. The interesting thing in America's Cup, the AC-75, which is this class of boat, is that you never see the sails out like I was drawing in that points of sail, right? They're always within a very narrow range because they're so fast, right? The apparent wind is always a very close angle, even if the wind is from behind, right? You add that vector of the speed they're going, and then you get that small angle. So the sails they never go out of the hull. There's a track there and it's pretty limited, which I find very counterintuitive coming from very slow sailing boats. And the maneuver is really important because when they turn, right, the speed decreases and they need a certain lift coefficient for the turn that's higher. So that's the 1.3 lift coefficient compared to the other much smaller ones, all right? And there's different cavitation constraints because there are different speeds. So this is our main result here for the optimization. So what I'm showing here, the first 3 are the first 3 points. We're optimizing the shape. Of course, the shape needs to be the same for all because we don't have a morphing airfoil, but we have a flap that changes. And we're optimizing the flap position for every condition, okay? Except the maneuver one is fixed to a certain one. And so this animation so the starting point was actually a previously optimized one. The initial one that they gave us was very different. And what we ended up with was a pretty unique shape in terms of relative to what they knew before. So this, I think, a nice example of optimization coming up with something different. And you can see here, the total drag is greater than before. But we satisfy the cavitation constraint, which the previous airfoil did not, okay? And you can see everything is under the line there, which is what we wanted. For these higher speed conditions, the flap is actually deflected slightly up, okay? Which is something consistent with the experience there. And this is the maneuver condition where we also limit separation, right? So this is comparing the 2 shapes, the initial and the final one. You can see again satisfying all cavitation constraints. Now, one thing that's not shown here is that in optimization, those of you who took my 588 course remember line search, maybe, I hope. And in line search, some crazy stuff can happen like this. So these are actually solutions that you have to do in the CFD, intermediate points in the line searches, where it asks for something that a designer would not, okay? So that's why our CFD needs to be very robust. So looking at some of the features of the airfoils, so compared to the baseline, so this baseline is actually the one I was talking about from a previous cup. And we compare it to that. So our foil has a flatter surface, right? by the leading edge and also aft camber. So this implies more lift without cavitation of the leading edge. So basically, you're filling that up to fill up the CP distribution to get that lift there without too much curvature in the top, so that we don't get a peak in a CP. Then also, there's also this leading edge carving. So this is a camber on the lower surface of the leading edge. So this again gives us more lift without cavitation or flow separation. And also, it has a side effect of getting this nose up moment, which you might counteract with other means. Okay, also the lower surface concavity by the hinge here, it mitigates suction when the flap is negative, right? So remember I said that when you have at higher speeds, the flap is actually up, so we don't have too much lift. And that prevents too much suction there. And finally, for a big part of the cavitation buckets of the higher speeds, we have this flap up operation, right? And that has nice characteristics because you get a greater range in CL without penalizing the CP min, which is the indicator for cavitation. And this also enables this coupled to the leading edge carving. So there's different characteristics there that are very different from the previous generation foil. Looking at the cavitation bucket, we can compare the previous one to the new one. So the dashed lines are the old ones, and the green ones are the new ones for that particular configuration. And you can see that it increased the cavitation speed significantly, right? And this is without much penalty in drag, okay? One caveat here is that we might actually not want to just remove cavitation altogether, right? Because there's a trade here that might be made, which is accepting some cavitation at higher speeds, but improving the performance at other conditions substantially, right? We weren't able to make that trade because we don't have a model for drag or lifts after cavitation happens, because that's basically physics that we don't model. We need to model the interface between the vapor and the water. It gets really complicated. Okay, but nevertheless, we're able to do this without drag penalty, and it's a useful result. And we also looked at what we were able to look at was different trades in how much we constrain cavitation, from no cavitation constraint to fully constrained. And this study resulted in these results here. And it's really nice to see. We see the lighter color ones is without cavitation, and you can see as you increase the cavitation, we can do that continuously up to 100%. We flatten out, and we can see the effect on the airflows. When you superimpose here at this scale, it doesn't look like much, but in hydrodynamic, aerodynamic shape, small changes make a big difference in drag and so on. And this is where optimizer can really shine. It's very subtle combination of small changes that make a big effect, right? That doing manually is very, very tedious and requires a lot of expertise. All right, so now some features here when you increase cavitation constraints. So again, the more cavitation or the more reinforced cavitation, the flattened upper surface by the leading edge and aft camber, and also the leading edge carving becomes more pronounced as well, and the lower surface concavity aimed by the center here is also more pronounced. So this is consistent with what we were finding before. Another study we did was to do different flap lengths. So they wanted to know, okay, what's the optimal flap length there? And you can see here, not very surprisingly, the bigger the flap, the better, right? But then we are limited by the hinge moment. So you have the bigger the flap, the larger the hinge moment, and also structural integrity is affected there. So in the end, they decided to go with 40%, and actually everybody in the cup converged to 40% flap length or around there. Again, for this study, all cavitation constraints were satisfied for the different flap lengths as well. Right, so that was the end of the 2D effort, right? And that was successful, contributed a shape that they ended up using. And then we went on to do some 3D work. The 3D work was way more challenging. I'd say more challenging than anything we have done with airplanes, okay? Part of the reason is, well, first of all, it's not symmetric, right? So it's at an angle there. And different depth require different meshes because you have different positions of the surface. And if you're going to do it properly, in some instances, the tip pierces the surface, and then you might get ventilation and so on, which we don't have a model for, right? So this became very challenging, but we did get some results. In the end, the flow physics wasn't quite right, so they were not used. But this is one of the figures we made, like the 3D full foil canted, and plotting the CP. And here you can see a hotspot for cavitation there that I want to remove. Our optimization was able to reduce that somewhat. But again, in the end, the physics didn't quite match. So that's work to be done in the future. There's a lot of potential for doing 3D optimization, like I showed you. It's possible in airplanes, should be possible here as well. Now I'm going to switch directions a bit and talk about the research done here at the University of Michigan that preceded all these efforts. So the consulting work wouldn't have been possible without all this background research. And here I have to thank Professor Julie Young, who used to be a professor here in naval engineering, who got me into this hydrofoil design optimization business. We have co-advised a sequence of 3 students, and the third one, which is Galen here. We actually did the aerostructural, hydrostructural optimization. So this is the same framework I showed before, but now it's coupled to a structural solid, okay? So now we're actually going to find the deflected shape of the foil, and for each flow condition, because they might be different depending on how flexible it is, and then do optimize that shape considering structural strength as well. So we did this hydrostructural optimization. This is a simple foil. We have these free-form deformation variables, and now we're actually modeling not just the CFD on the outer mold line, but we're modeling the structural stresses and deflections of the whole foil. And this is solid, by the way. There's no wing box like the one you see here on the atrium. This is just solid, okay? And in this case, it was solid steel. And this was the work of Nitin Garg, who was a PhD student here, this PhD in naval, co-advised with Professor Julie Young and myself. He ended up going to work for the America's Cup team INEOS for the last 2 cycles. So that was good to see. So this actually got built by the Australian Maritime Museum College, and they built it and tested it in a water tunnel, and as part of our collaboration. And we published this paper here where we show the results here of the baseline NACA 0009. Okay, so not a very good hydrofoil. Obviously, it's symmetric and whatnot. And then we have our foil optimized with cavitation constraints. So not only did we move the whole drag polar to the left here, reducing drag at all conditions, but we're also enforcing cavitation, which this one was not enforcing. So you see cavitation here on the baseline one, no cavitation on our foil. And you can see a pretty good match here between the experimental results and our numerical results for the both optimized and baseline. The next student we co-advised was Yingxian Yao, and she did also a series of problems in hydrofoil optimization, including this T-foil. So now we're talking about 3D with the junction, and this shaping of the junction and simultaneous shaping of the foil there is really critical to because you tend to get superimposed flow there that is accelerated by both surfaces and therefore more prone to cavitation and also separation. So in this case, we have a constraint on separation and cavitation. You see cavitation of the baseline shown in orange here, separation shown in green, and you can see our optimization. You see a few false steps there, but eventually eliminates cavitation and separation completely. And it does this by cleverly shaping the foil and the vertical structure there as well. And next, we have Galen's work, cleverly with Vinci, and then did some more work on his own. In this case, doing platform optimization of the hydrofoils. And we found that a nice sweeping shape actually was very beneficial, not just for drag, but also cavitation as well. And we also made it of composites. And you can see here a substantial improvement in the cavitation bucket relative to, of course, the 009, not a very good one, but a decent hydrofoil that many designers use with a section, Epler section, with this number. We got substantial improvement over that hydrofoil as well. And here, instead of using a constant airfoil shape, this is optimized at this section, and the whole platform is optimized. So we got a nice cavitation bucket there. And this is hydroelastic, so it's considering the flexibility of the composite and optimizing the composite structure there as well. Starting with a lot of cavitation there, and then no cavitation for the swept one. And this was built, and it's now again in the Australian Maritime College, and I believe Galen's taking a trip down under to Australia this summer to make sure everything gets tested there. And hopefully we'll get as good results as before. No pressure, but yeah. All right. So in conclusion here, so we developed this workflow for cavitation constrained hydrofoil design with flaps, both for 2D, some progress on 3D as well. And this really accelerated the discovery of new designs. And we experienced that in the actual cycle of America's Cup, of the design cycle, which are a very challenging environment. You need to have tools that are mature enough to really deliver there. In terms of design, we improved the cavitation buckets with multi-point optimization. I didn't show these results, but we were verified with Xfoil by no other than one of the co-authors of Xfoil, Harold Youngren. So I think those comparisons are very good. And we basically have a minimal drag penalty for satisfying cavitation constraints. And finally, the flap study revealed bigger the flap, the better. And the end result was a flap of 40% for the America's Cup boats. Thank you.